Hello everyone, in this video, I'm going to go over the AETC Workshop 10 for Chem 118B. So this worksheet is about Diels Alder Cycloaddition, and where the Diels Alder reaction, we have a diene and a dienophile, where the diene is the nucleophile and the dienophile is the electrophile. So a diene is a molecule with two alkenes in the S-cis configuration like this. And the dienophile is an alkene that loves dienes. So this is the electrophile that gets attacked by the diene. And usually when we do the predict the product questions, we draw the endo product where the outside groups of the diene are cis to the electron withdrawn group of the dienophile, and the inside groups of the diene are trans to the electron withdrawn group of the dienophile. So we see here in this example, this diene here has this methyl group that's on the outside group, whereas this diene here has groups are in the inside group over here. So usually the outside groups are cis to the electron withdrawn groups on the dienophile, like in this case, where they're both cis and dash. And this right here overpowers the steric hindrance factor because of the p orbital interactions that increases the resonance, which overpowers the steric hindrance factor. So then to predict the product and determine its stereochemistry, if both of the starting materials are symmetrical, then your Diels Alder product will be a musyl product. And if one of the starting materials you have, either the diene or dienophile, is an asymmetrical molecule, then your product will be a pair of enantiomers. And if both starting materials are asymmetrical, then you have to consider the regiochemistry, which I will show later on by doing the resonance and charge explanation. You will have one or two pairs of enantiomers depending on if you have one or two products. So first we see here, this is our diene with two in groups, which are the methyl group here. We have the dienophile here with two electron withdrawn groups here. And to tell what is an electron donating group or electron withdrawn group is to see the atom directly attached to the functional group. So we see here, this is an R group, which is an EDG, or electron withdrawn group. And in this case, we see this carbon here, which is partially positive. And if an atom is partially positive, it's an electron withdrawn group, or EWG. So we have an EWG here and an EWG here. So the mechanism of the Diels Alder reaction includes three arrows, where we make the new bond between these two carbons, and move this double bond to this existing bond over here, making the double bond there. And I highlighted the carbons to keep track of what carbons are attached to which. We see here that this in the ring right here, which is the N group, this would be trans to the EWG from this endo octi mnemonic. So if we put this as a wedge, then the EWGs would have to be dash, and this is trans. And since we have two symmetrical molecules, the diene and dienophile are both symmetrical, then we will end up with a mesyl molecule. And now let's move on to part B. We see that we have diene and dienophile here. It also matters when you draw the product where the EWG lands. It could either be on the top side or bottom side. And to determine that, I do the resonance, which I see here. Since this is an EDG, is donating electrons to this carbon, which is going to do the resonance here and donate the negative charge over here. Since this is an EWG, I withdraw electrons and kick the carbonyl double bond onto that oxygen, giving us a positive charge here, negative charge there. We see here that the negative and positive charges are attracted to each other. So this is the correct configuration where the electron withdrawn group, EWG, is on the same side as the EDG over here. So when we do the arrows, we want the two groups to be adjacent to each other. So since this is an outside group and this is the EWG, we want the outside groups to be cis to the EWG. So I made that as a dash. And since these two molecules here are asymmetrical, then we would have an enantiomer as well. So in this case, this is our diene, this is our dienophile here with an extra bond. So I would redraw this, a dienophile, in the usual form that we do the mechanism of the Diels Alder in. I do the regular arrows, and since the dienophile still has a single bond there, this is an sp2 carbon, which maintains the planarity of this two electron withdrawn groups here, where this inner ring here, I made that as a wedge over there. And then let's move on to the next one. We see we have a diene here with one electron donated group here, which is why I donate electrons here, kick up the double bond onto that, and giving a negative charge there. And this NO2 here, I flip this upside down to withdraw the electrons from the dienophile, giving a positive charge there, which is important because we don't want the NO2 group to be facing upwards, because if it were to be facing upward, the charges would not be aligned. It would be misaligned, since if the NO2 was on top, then a positive charge would be in the bottom, we were pulling each other, and a negative charge would be on the top, we pulling each other, which is why I want to flip the NO2 group going down, which aligns the positive and negative charges together here. So I redraw this here, do the mechanism of the Diels Alder. This is an outside group, which is going to be cis to the electron withdrawn group here. And this right here is not considered outside or inside group, because this is part of the sp2 carbon of the product. So in this case, we have an enantiomer because both of these molecules here are asymmetrical. So then now let's move on to the next one. We have an EDG here and an EDG here, which can do resonance. But this EDG here with the oxygen and 2 lone pairs is a stronger EDG, which is why you get this major product, whereas this is a minor product. Because let's look at the donating effect of the oxygen here. We have a resonance structure donating into this double bond, moving this double bond over here, giving a negative charge to that carbon. And then this is an electron withdrawing group, which will withdraw electrons. We see that these charges align. We see that the alkoxy group, the OR group, is on the same side as the electron withdrawn group, which we see here. They're both dashes because this is a outside group, which is going to be on the same side as the EDWG. But the R group we know is also EDG, so we could do resonance on the other way, giving a negative charge there, which means that we have to flip the aldehyde upside down to align the charges, which we see that the methyl group is going to be on the same side as the EWG. But since the methyl group is the in group, then that in group would be on trans to the EWG, which we see here. But since the EDG ability of the OR group is stronger than the EDG ability of the R group, then this would be the major product. This would be the minor product here. And also this would also be plus enantiomer as well, since both of these molecules are asymmetrical. Yep, plus enantiomer over here as well. So then let's move on to the next one. We see here, this is our diene. I withdrew this diene in the regular way. We see the mechanism. This is our dienophile with 2 EWGs here. We see that this diene has an electron donating group here that is in the out group, where we donate electrons, giving this carbon a negative charge, this carbon a positive charge. We see here, since we want a negative charge down here, we're going to withdraw electrons going down there, giving this carbon a positive charge to align the charges together. And then we do the whole mechanism over here, which we see this EDG is on the outside group, which is going to be cis to the EWGs here. Both of these molecules, well, one of these molecules, which is diene, is asymmetrical, giving us the enantiomer product, and the dienophile is symmetrical. So then let's move on to the next one. We see here this diene has 2 EDGs on one of the carbons, one out group, one in group. So we see that when we do the resonance form here, we have a negative charge on this carbon, a positive charge on that carbon. When we do the resonance on the dienophile, we want the charges to align. So we're going to give this carbon a positive charge by withdrawing electrons to this nitrile over here, which aligns the charges. When we do the mechanism, we get this out group, ethyl group. It's going to be on the same side as one of the EWGs, which is this one. And this in group is going to be a wedge. So since the 2 nitrile groups here are trans, not cis, then these 2 nitriles will also be trans in the product, same as the other possible product as well. And both these will be enantiomers because the diene is asymmetrical. So then let's move on to the ranking problems. So dienes are usually nucleophiles, which increases its reactivity if we add more EDGs. So the strongest EDG here would be this molecule here with the oxygen on 2 lone pairs here, which is able to donate electrons through resonance. The second most reactive diene would be this one right here, which we have 2 EDG groups where there's less steric hindrance. For this molecule here, this molecule also has 2 R groups, but there's steric hindrance because in the mechanism we see that the diene needs space to react with the dienophile that way, which we see the R groups here are getting in the way of that, increasing steric hindrance. And then this fourth one here is the next fourth reactive with no EDGs, no EWGs, because there's no electron donating effect that is going to increase the reactivity. And this is the last most reactive diene, because we need the diene to be in the S cis configuration, not the S trans configuration, which this is the S trans configuration over here. And this is locked into the S trans configuration because this is inside the ring. We cannot rotate it with heat because this is not in a linear chain. So now let's rank the dienophile's ability and reactivity. So since dienophiles are the electrophile, its reactivity increases with more electron withdrawing groups, where we see here this molecule one has 2 electron withdrawing groups, 2 partially positive carbons here, increasing its reactivity. The second one here has 2 electron withdrawing groups as well, which are the 2 nitro groups. And then the third one here only has 1 electron withdrawing group. And then the fourth one has no EDGs, EWGs. And then the fifth one has an EDG, which decreases its reactivity, whereas the sixth one has 2 strong EDGs that could donate electrons to resonance, making this the least reactive over here. So the reason why this over here is more reactive than the nitrile is because this EWG ability is stronger than the nitrile over here. We see that oxygen is more electronegative than nitrogen is, which is why oxygen can hold a negative charge better than nitrogen, making this a better EWG than nitrile is. So thank you for watching. Please like, subscribe, and share.